This is going to be a bit of a long journey, but I hope it'll be an interesting one. So let's get into it quickly. Now the problem is this: there's no way to model the high-level structural design of a system. Now, what do I mean by those things? Well, structural is the complement of behavioral. It's about how elements relate to each other and not about how to put the elements together to achieve some purpose. High level means we don't represent everything, but we represent those things which are most useful to represent. And a model is something that can be used in place of the original. So we all are familiar with the example of a blueprint of a house not being the house, but you can see it as a model of the house. Now, why do we want this? Because there's no shared language between a lot of stakeholders in a software system. If that system happens to have a functional design, we have to do ad hoc diagrams and analogies to show people what we're doing, and even then, the cost of misunderstanding can be high. So this is an effort to make that gap between technical and non-technical smaller and make communication easier all around, while not losing the things that make functional programming functional. Ideally, this is what we want. Express the structure of a functional design in a way that is useful to programmers and other stakeholders. But now we must ask ourselves two questions. What do we mean by functional design? And what do we mean by useful? Useful to who? Useful how? Let's start with the second question and talk about usefulness first. Programs, as human artifacts, have some meaning on a human level. Here we see some F# code to multiply a list elements by 1.15. That is its meaning to the program. But in human terms, in my country, this will calculate the sales tax on most common goods. So its human meaning is that it calculates our sales tax. Now, types help to encode part of that meaning. One of the good books on this is Domain Modeling Made Functional, and there are many other references about the same idea. But types don't encode all the meaning. Here I show a type that might mean insert into a sorted list, or maybe prepend to a list, or maybe even return an empty list if the specified element exists in the original list. So types show meaning, but not all the meaning. Useful models reveal meaning that is otherwise non-obvious, and even better models can be used to design things that don't yet exist, with the understanding that going from model to system will be a relatively easy process. Now, before we talk about design, I want to quickly touch on the relationship between a model and a specification. Now, a specification is a kind of model. It's a kind of very detailed, very specific model. It is so specific that it can often be used to generate the final product, at least in part. But it pays for that power by sacrificing usability. I don't think anyone can say that executable specifications are things that can be learned in a casual hour or two. Design, in the sense I'm using it, complements specification. It does not replace it. Now, okay, that out of the way, let's see what we mean by design. Now, the basis of all design is an underlying philosophy. That philosophy can't change. It must be invariant. It's what gives a shared perspective to practitioners. So for object orientation, that philosophy is actually Plato's theory of forms, which says that there are ideal kinds of things, which we call classes, and everything we see in reality is just an instance of these things, and the way to look at the world is as discrete objects and relationships between them. Now, no matter what object-oriented system you look at, this philosophy is there. It is invariant. It is a shared perspective. Now, obviously, as well, the theory of forms isn't how functional programmers see the world. The actual system logic or meaning is built on top of a philosophy. Without the underlying philosophy, there is no shared perspective. There cannot be shared meaning. Meaning evolves with a system, but can never be found outside of the underlying philosophy. So now, if the theory of forms doesn't work, what underlying philosophy might work for functional programming? Ludwig Wittgenstein is one of the most celebrated philosophers of the past century, and it turns out that he came up with the idea of describing reality, specifically the social reality that humans exist within, as a language game. It's a very interesting philosophy, and I'm only going to give you the barest bones of it from what I think is most relevant to least relevant for our purposes. And to take you through it, I'm going to describe a combinatorial parser system as a language game. Now, every language game has some purpose and may have implicit presuppositions. A parser has the purpose of parsing text and may have some presuppositions, such as an input can have an end, or new lines are important, or even characters can be more than a single byte, and so on. Now, words have no independent meaning outside a game and may have specific meanings for only that language game. So for a parser, parse takes on a special meaning, so does stream, and so on. And inexact meanings are fine. Meanings are only separated to the extent needed to avoid misunderstanding. So when we tell our parser to stop at the end of the line, that means the new line character, or the return character, or maybe it even means end of input. That's fine. We don't care. We all understand what it means in context. Words may have multiple independent meanings, and an unused word is meaningless. The FParsec parser system, for example, has optional having two possible meanings. Number one, it can mean parse and wrap the result in an optional type. Or number two, it can mean try to parse, but if it isn't there, just ignore it. It's optional. Now, both of those meanings are perfectly valid. This slide contains some still relevant but more broad picture takeaways from Wittgenstein's philosophy about language games. I'll leave them for the questions or later perusal if you're so inclined, but what I want to draw out is the text right at the bottom of the slide. Fundamental functional programming techniques have natural language analogs. We compose words all the time. We relate them to their original contexts. We have no problem passing entire concepts around in a single word, and so on. Now, those aren't exact mappings. They're analogs, but they do exist, and I think that's important to think about. But now we run into problems, because an analogy can only take us so far. As Perlis said, computers don't use natural languages, and certainly things can be expressed in code that are quite difficult to describe in natural language. So going between a language game and an actual programming language is trial and error, probably with more error. But what if we found a language that we could play a language game in, but which isn't a natural spoken by everyone language, and which was closer to programming than natural language? It turns out that mathematicians have a constrained language that they use and have effectively used for centuries. It has definitions, presuppositions, adaptive meanings, rhetoric, and it is in use today in any mathematical paper or textbook that you'd care to read. And it is sophisticated enough to play language games in. And functional programming, unlike object-oriented programming, retains very strong links to mathematics. So the idea is this. We use the constrained language of mathematics to give us our fundamental constructs, and we use the philosophy of language games to help us think about how to use those constructs. And the result is a language for functional programming design, which leads us back to the ideas of design and usefulness. If we are going to model something, what kind of useful things do we want to be shown by that model? Well, let's take some inspiration from languages. We have dictionaries and thesauri and etymology. All of them answer different but important questions. What words exist? What do they mean? What words are similar? What is the ancestry of a word? And there are also some other things we use in languages, like grammars and exercise books and so on, but this should be enough to start us off. Let's now look at how this all ties together with a quick case study. I'm going to show you a high-level structural design of FParsec, which is quite like Haskell's parsec, but it's written in F#. Now, I'm not tied to this notation, but I do quite like it from a visual perspective, and I did arrive at it through an actual process, which I'll be happy to talk about, but which is really not relevant right now. So let me just introduce the salient points of this notation. Now, what we see in these nice spiky shapes over here are symbolic definitions, and next to each symbol is a meaning. And then we have this shape over here, which looks like the spiky shape, but with a dot in it. And that means any value or any type. And behind these arrows over here, we have different cases, and each case relates to the definition. So if we look at this over here, we see that if those parsers happen to be successful, then this is the result on the right-hand side. And if it's anything else, as indicated by the underscore, then this is the result, a failing parser. Now, what we have here, you might realize, is a dictionary. Each definition has some meaning next to it, which is written in English for some and with notation for others, and a mix of the two, just like mathematics. Only notation that's already been introduced is used if you read from top to bottom and left to right. So just like a regular dictionary, there is some human sensible ordering that we can actually use. Now, where do things come from? What is a specialization of what other thing, and what can structurally be seen as being based on something else? That's what we add here with etymology. When something has a bold border, that means it's so fundamental to everything else that it would cause spaghetti lines if we tried to draw them all out. These are the really important definitions if you want to look at the roots. And just like in English, where you have, for example, things like pre and post prefixes, well, if you don't understand what pre and post mean, then, you're going to have problems with a lot of other English. The diamonds show specialization. Each of these three parsers with the white diamonds, the not filled out ones, is actually just a special case of the foundational one with the black diamond. These circles show extensions. What uses what other thing as foundational? The black circles show the foundation. The white shows the extension. Of course, some things can have more than one foundation, and that's fine. So for example, here we have between having a foundation of the parser whose output is discarded. It discards the first one and the third one, and a parser producing results from other parsers. So now we know where things come from. Now with this, we've added two blocks in the bottom right as a thesaurus. Here we show things that we think semantically might be useful to group together, even if they have no basis on each other and they have no common ancestor. Now the second block I think shows that quite well. Those two have no common ancestor. Nevertheless, semantically, from a design perspective, they are related. All right. So now I'm not married to this notation. Maybe you think it's ugly. Maybe you already have a better idea for a better notation, and that's fine. Or maybe you love it, and that's fine too. The actual contribution of this research, though, as I see it, is laying out a sensible philosophical basis that we can use. Finding a reasonable language, mathematics, that can serve as our touchstone, and identifying bits of what we might think are useful to know about a design. I'm not trained as a designer of notations, and I rather look forward to someone coming forward to tell me all of the terrible things that I'm doing, as long as they provide their own alternative and show me that it works or looks better. Now, here are some reserved suggestions for the notation, but again, not really tied to any of these. Now, assuming that you think the work is worthwhile, there's plenty of work to do in this space. Now, these questions are just a few off the top of my head. You can probably think of more. Symbols and namespacing. What do we do when we want to use the same symbols in another context? What do we do when we want to take our parser and actually use it in a program, but our program uses, let's say, the plus symbol? What do we do? Is there some import? Is there some way of redefining? What do we do? Symbolic overload. What is overwhelming? What is, you look at it and you just want to go and cry in a corner? What is rich? What does that mean? What is a rich set of symbols? What is sparse? What is poor? What is too little? What design guidelines should there be for symbols? And what is modeled depends on what needs to be modeled. That's a core aspect. But is there a guideline set of things that needs modeling for every system? And what do we mean by need? And if we say it is a need, why would it be a need? What defines that need? Now, I plan on answering some of these questions, or if I can, maybe even all of them. So stay tuned. And of course, there's more to do in terms of tooling, in terms of refinement, in terms of application, and so on. There are case studies, and I'm hiring, which means, since I'm an academic, that if you want to do some master's or doctoral research about this, please feel free to hit me up. I can promise all of the benefits of the academic life as soon as I remember what they are. And if you're a company that is interested in working on these notations with me, then please also get in touch. Empirical evidence and collaboration is very much desired, even if it doesn't quite show what I think it should show. So with that, it leaves us about 10 minutes for questions, I hope, and I at the end, I hope to see you in the lounge. Thank you for your attention, and if you have questions, I'm ready for them now.
Okay, very much thanks for your presentation on this difficult topic. And there are some questions in the reference to examples. What do you mean by discrete grouping and discrete cases?
That's a great question. Thank you. When I say discrete cases, I mean basically a sum type. When I say grouping, I mean a product type. These are basically the two types that you will also find in mathematics, and as you know, they can be used to describe everything in the whole world. So we don't need to have other things other than sum types and product types. Yeah, I hope that answers it. I mean, in the feed, I've got it open. Let me know if I haven't answered, or you have, or just raise a hand.
Okay. And the other question in the Q&A session is, what would be concrete examples of a program or a design expressed in this notation? Do you have any evidence that it works? Is it used in a concrete example, or?
Well, there it is. This is FParsec. If you go and you take this diagram and you look at FParsec, and you say, well, does one map to the other? You'll see, yes, it does. In fact, this is what the design of FParsec is. At a high level. Now, the question's a good one, but it's also a chicken and egg problem. Because the thing is that one can't do a notation out in thin air, floating with no application. But at the same time, one has to have, so you have to design the notation with reference to some cases. So here's a case, but you can't design a notation based only on cases. Because if you do that, you risk the problems which are quite well identified with UML and existing modeling, which is that you get very language specific. And because you get very language specific, you become unable to actually express things that are found in all languages or other languages. You don't have a theoretical foundation. All you're doing is, for example, taking Haskell and making it visual Haskell, which is not what we want. You want something that is a common language.
Yeah, but if you say, I'll take this parser library and make a picture of it or a design, that's still kind of reverse engineering. What I think the question aims is say, well, design a system by your UML equivalent, and then implement it and see how good this blueprint is.
Well, that's something that I plan to do eventually. As I say, future work. The first step is seeing, can it represent what is there? Because I mean, I have done it the other way. For example, with to do MVC, which is the well-known web application example. But then one runs into the problem of, well, did I do the design specifically so that it would be implementable in that way? And you're the same person doing both, and how can you get rid of that? So you can't be the experimenter and the one who's experimented on at the same time. Does that make sense?
Absolutely.
On the other hand, look, I'm very happy for someone to come and work alongside me and basically do the design independently, do the implementation independently, and see. And I think there's some good publication opportunity in that as well, whichever way it turns out.
Mm-hmm. Okay. Another question still in the Q&A session is, have you thought about expanding UML? And was that inappropriate, or?
Yes, terribly inappropriate, doesn't work, completely object-based. I mean, it's literally created by a group called the Object Management Group. A whole bunch of things in UML just do not translate and are completely irrelevant. Objects being core to everything is one of them. I mean, look at what's in front of you, find the object. You know, it's not there.
No, that's correct. But the UML is just a collection of existing tooling. So there are all state charts and things like that, which I just collected and then called UML as the unified language.
Indeed, but there are only very few structural UML diagrams. The case in point being class diagrams. Now, if you take class diagrams or any of the other structural diagrams and try and find the structure in a functional design, you won't find it.
Yeah. One final question, perhaps, before we move to the next session is, it would be interesting experiment to attempt to use to model non-academical everyday business problems, like the video store example.
Let's do it. That's my answer. Let's do it.
Yeah, I'll think that to be convinced that this works, that it's worthwhile to do it on a real world example which is not existing, and perhaps a small real world example, but still something new.
Absolutely. I mean, for what it's worth, you know, when you want a parser, you go to FParsec. When you want a parser and you're using F#, you go to FParsec. That's a real world used in production system. Happy to apply it to others, but I don't think it can really be said that, you know, can't model a real system, you know, if one does. But yeah, let's apply it elsewhere. Absolutely.
Yeah. So that would be very interesting and worthwhile to see. Is there something more in the feed? Well, people want to try it out, which is great, of course, for new ideas. So you have at least succeeded in convincing Daniel to do something with this. Wonderful. Yusuf, once more, thank you very much for this presentation on this interesting and challenging topic.